Hello again, wonderful people. Welcome to Cosmology Talks. This is another talk in the CAMELS series. This one is by Leander Thiele, who is a PhD student at Princeton. As it is part of a series, there's no intro to CAMELS in this talk. If you want an intro, it should be on the screen right now, or if not, it's in the description. Leander is talking about using spectral distortions to constrain baryon feedback. Recording these intros, I'm starting to notice a trend, which is that CAMELS is good at, or at least trying hard to, constrain feedback, which kind of makes sense to me because baryon feedback is very, very messy, but presumably has hidden trends that the machine can find. They find that spectral distortions can constrain baryon feedback very, very well, which again for fundamental cosmology is super interesting because it removes that known unknown. And for astrophysics, it's also very interesting because it helps us know how AGNs and supernovae are acting within galaxies. So enjoy. Welcome to Cosmology Talks, Leander. Do you want to start by telling us about your work?
I'd like to talk about our work using CAMELS on spectral distortions and how we can use them to constrain baryonic feedback mechanisms to quite high precision. And this is joint work with all the people listed here. So we use CAMELS to measure the Compton Y monopole distortion and its relativistic correction. And we establish the connection between the astrophysical parameters in the simulation and those spectral distortion signals. And using these measurements, we can then show that a near future measurement of those distortions would provide us with very tight constraints on certain parameter combinations of these baryonic feedback parameters.
In slightly more detail, what questions were you trying to answer? Why was each question important to solve? What do we gain as a community by having solved them?
We're basically at the point now where baryonic physics is really a major impediment to our understanding of cosmology. For example, here I've plotted just the matter power spectrum in different hydrodynamic simulations. And what you can see here is that there's a quite substantial difference between the power spectra that you get in those simulations, depending on the feedback that the simulations implement. So what we need to do is understand these feedback mechanisms. And one way to do this is to look at these spectral distortions, which are essentially measures of the thermal energy in electrons and some sort of mean temperature in the observable universe. And what you can see in this plot is that CAMELS really spans a huge range in this parameter space, orders of magnitude, whereas a conceivable experiment like PIXIE or the European analog would really place a very tight constraint in this parameter space. So what you could do would be to really differentiate between different subgrid implementations.
I see. So it really is that at the moment we're that uncertain about where we lie in this kind of diffuse banana.
I should qualify this in the sense that CAMELS really tries to go very far into crazy directions. So some of the CAMELS simulations are certainly not going to represent our real universe. But even if you discard those, you still are left with quite a wide range of predictions.
Because I guess even Illustris and Simba, presumably they both wanted to simulate something that might be reasonable, and they are quite far apart, at least compared to the PIXIE.
So if you look at the green and yellow markers, which are these large boxes, they tried to get as close as possible to the real universe, and you see that they are quite far apart. Along the way, we really have to deal with a problem in CAMELS, which is, or not a problem, it's a feature. The fact that the CAMELS simulations are quite small in volume, because otherwise you can't run as many of them. But these small simulation boxes mean that there's huge cosmic variance. So in fact, some of the scatter that you see here is just cosmic variance in the small boxes. So as a sort of technical point of this work, we really needed to think about ways to get rid of this additional scatter.
I see. Oh, that's interesting. So it's not just that different CAMELS simulations are using different feedback parameters, but even the same feedback parameter run for two different realizations could be quite different on this.
Exactly, yeah.
Okay, cool. So do you want to get into the details, pick a few specific statements about your results that are interesting and help us to understand what they mean?
I guess the first result that we have is really connecting those feedback parameters. There are 4 of them with the spectral distortion signals. So here I've just shown as an example in Simba, the Y monopole, so the all-sky average. And you can approach this problem in different ways. So one of them would just be to look at the 1p set in CAMELS, which is for a given initial conditions set, we just vary these feedback parameters and we look at how our observables change. And these are the blue data points. But we can also take the LH set, where in addition to the feedback parameters, we also vary cosmology and the initial seed, so the initial conditions. And what we did is we trained a neural network to interpolate through the LH set. And in the paper, we basically argue that this neural net is more robust than the 1p set because it implicitly marginalizes over the initial conditions of the random seed. So this is actually what we use in later parts of the work.
You might not know the answer to this question because maybe I need to ask the people behind Illustris or Simba in this case, I guess. But is ASN1 equaling 1 kind of their best guess of what ASN1 actually is?
Yeah, that's right. So the feedback parameters scale from the fiducial value. So 1 corresponds to the fiducial value. But yeah, I would say that there's substantial uncertainty on what it should be. Yeah. Okay, so using those neural network interpolators, we can now do a really simple Fisher forecast. So we are using this PIXIE covariance matrix that marginalizes over all foregrounds and so on. And because we only have 2 measurements, but 4 feedback parameters, we can only consider certain parameter combinations, right? Because you can't measure 4 values from 2 data points. So the best constrained orthogonal combinations are listed here. And what you can see here is that for both Illustris TNG and Simba, we can constrain at least 1 parameter or 1 parameter combination to 1.5% in the case of Illustris TNG and 0.2% in the case of Simba. And for Illustris TNG, because the dependence on those feedback parameters is a lot smaller in this simulation, there's no second parameter that we can really constrain, right? But for Simba, there's actually a second orthogonal combination that we can constrain at around 8%. So in order to put this into context, you have to remember that the fiducial model, as I said, is 1 for all parameters. And well, it's hard to really quantify the current uncertainty, but it's probably about a factor of 2, which is also about the prior range that the CAMELS team chose. So if you consider these things, then a PIXIE-like measurement would really provide a dramatic improvement in the knowledge on those parameters.
Imagining a future scenario where PIXIE has run and one has therefore constrained A Illustris and A Simba to be whatever they turn out to be. Presumably Illustris and Simba are actually doing something slightly different under the tin. So A Illustris might be a slightly different value to A Simba. But are they then going to produce cosmological simulations that are at least statistically equivalent, or even if I started with the same initial conditions, kind of actually equivalent? Or are they still going to have some sort of lingering difference that is just not affecting the spectral distortions? Yeah,
so, certainly you could produce Illustris and Simba runs that give you exactly the same spectral distortions, but other properties are going to be different. So, yeah, it's going to be very interesting to combine some sort of measurement of the spectral distortions with other probes.
Yeah, and I guess if the spectral distortion required A Illustris equals, 1.2, but some other, X-ray temperature measurement required 1.4, it would just mean that Illustris needs, with this hypothetical future better data, needs to rerun itself with more parameters, I guess.
Yeah, so yes, we are certainly limited in terms of the range of predictions that we can make by choosing those 4 parameters. There's certainly more that you can take.
I guess the hope is that they're doing the right thing, and therefore once you start measuring these parameters with multiple observational probes, that they give the same value, and that would give a lot of confidence that these hydrodynamical simulations are actually modeling the universe correctly.
That would be great, yeah. Although I wouldn't bet on it.
What should we, as a cosmology community in general, take away from this work? How should we update our beliefs? What should we change about what we work on?
One sort of fundamental thing is to take these spectral distortion monopoles seriously. So I think cosmology is sort of dominated by, thinking about power spectra and anisotropies, right? Because this is how the CMB works. But really just measuring the sky average of those signals also can tell us something really interesting, and is certainly complementary to these higher moment statistics that people usually consider.
Okay, cool. And then the final question, what still keeps you up at night about this general area of research, and what would you want to discuss about it with other experts, either within CAMELS or even outside of?
The fact that only 4 parameters have been buried. So this is maybe okay for, the contribution those signals receive from halos, but there's some small contribution from outside the halos that is perhaps more affected by other astrophysical parameters that were not varied in CAMELS. So this is something to be mindful about. Then, our interpolators are limited by still relatively small number of simulations that we have and the huge cosmic variance in them. And something to look forward to is certainly how we can improve these constraints that I've shown by combining with other probes. And there's a lot of very interesting work going on around CAMELS and outside, looking at other measurements that we can use to constrain astrophysics even more.
Well, thank you, Leander, for the great work and great talk.
Thank you very much for having me.
Thanks for watching. I hope you enjoyed that. There will be a live discussion of this and all the other CAMELS talks sometime in February or March, with all of the speakers present as well as some invited adjacent experts. So if you want to be informed about when that happens or any other mini workshop associated with any other cosmology talks, get in touch and I'll put you on a mailing list. If you want more CAMELS talks, there's a playlist in the description and a video being suggested on the screen now or soon. You could also perhaps watch Deanna Hooper's talk, which was about using spectral distortions to look for new physics. It's a very old talk from 2020, so it's less polished than some of the more recent ones. And it's made me realize that I should probably have more talks on spectral distortions, given that that's how far back I had to go to find one. But it's still interesting research, and Deanna presents it very well. In the meantime, if you like this, don't forget to subscribe and click like so that YouTube knows to share more similar stuff with you in the future. And have a great day.